Let's compute a characteristic mean free path through air. So remember, the mean free path tells you the average distance that a particle will travel before experiencing a collision. And imagine that we're given air as an ideal gas of temperature 300 Kelvin and P equals 1.01 bar. So sort of standard conditions here on Earth. We have to be told that the cross-sectional area of air molecules is about 3 times 10 to the minus 19 square meters. There's no way that you could get that number unless you actually did something like a calculation involving a mean free path. So generally speaking, you'll either be given that value or you'll be given the mean free path so that you could calculate the area. But in this case, we're told the area. So what are we trying to calculate here? The idea is that we have a bunch of air molecules and we're going to have other particles zooming through and sometimes running into them. So that particle didn't make it far. This one makes it pretty far in. Another one doesn't have much luck at all. The idea is that there will be an average distance that a particle will travel before it will experience a collision. You could imagine doing this experiment hundreds or thousands of times and measuring, or you can use first principles to figure out what the mean free path must be given the temperature and pressure and cross-sectional area. Okay, so the mean free path, very simple formula, is just 1 divided by the number density of targets. So that would be the number density of all those little black dots there, and we'll have to talk about how to calculate number densities in a minute, divided by the cross-sectional area per target. And again, the cross-sectional area, you can imagine the effect is if they have really big areas. If you're trying to pass through a region filled with beach balls, it's tough to do that. If it's a region filled with golf balls, you have an easier time because their area is smaller. The number density also makes sense. If there's a lot of particles you have to pass through, you won't get far without a collision. If there aren't many particles, if the number density is low, you can get pretty far before you experience a collision. So both scalings make sense. So let's first focus on calculating the number density, and ntarg has units of number per volume, right? We want to know the number of targets per unit volume, so we can construct it from big N over big V. Well, you may have noticed in the kinetic theory discussion that actually we can come up with a new version of the ideal gas law that involves Kb. So little n, here the number of moles, divided by big N, the number of particles, whatever that is, in some substance, times R bar equals the Boltzmann constant. And what that means is that you can rewrite the ideal gas law as P big V equals big N KT. That's nice because now we don't need to have two things with a symbol little n that mean different things. Okay, so now we have P big V equals NKT. That means that N divided by V must be the pressure divided by the quantity, Boltzmann constant times the temperature. Well, that's nice because we just said that from dimensional analysis, the number density of targets should just be N over V. So that means that it should just be P divided by KT. All right, great, we'll keep that. Now we can put in our values. So we know the pressure. We'll put it in SI units, so it's 1.01 times 10 to the 5th pascals. Kb is a constant, and then the temperature is 300 Kelvin. That tells us that the number density of targets is going to be a really big number, 2.44 times 10 to the 25th targets per cubic meter. Is that for real? Well, yeah, it's air, so there's a whole lot of air molecules out there. Indeed, you can have a number that's sort of an order of magnitude or 2 bigger than Avogadro's number per cubic meter. That makes sense. Now, the nice thing is our calculation is pretty straightforward. Mean free path is just 1 divided by this number density we just calculated and the area of the targets. We're given the area of the targets, so we put in both of those values. And we find that the mean free path in air under normal conditions is about 10 to the minus 7 meters or 100 nanometers. Now, you can't really take this number very seriously in the sense that a cross-sectional area only has one significant digit, but this does tell you a characteristic length over which a molecule would move through air before experiencing a collision. Now, as I noted in lecture notes, this may actually be a slight overestimate. If the air molecules are moving around, which they certainly are at 300 Kelvin, then you can imagine this might be reduced by a small factor. But if you say that the order of magnitude is 100 nanometers, you're probably not too far off.